Hi, welcome to this video series on program synthesis. We have been looking into different problems and how to synthesize them mechanically using program synthesis techniques. I was looking into a simple problem in a different context. My goal was to come up with a function that checks whether an input number is a power of 2 or not. For example, as simple as say 4, for example. 4 is power of 2 because it can be written as 2 power 2. And 9 is not a power of 2 because we cannot write as 2 power something. Okay, so given input like 4, the program should say yes, answer should be 1. For 9, it should say 0 because it's not a power of 0, not a power of 2. Okay, so you would like to be able to check whether a given number is a power of 2 or not. And it seems to be such a very basic problem. And I was just looking online a little bit, right? And I got a hit on the Z3 page. The Z3 is the SMT solver from Microsoft. And I have been using that for many analysis. And it showed me one interesting pattern. It said, okay, a number X can be considered as power of 2 if X and the bitwise and X minus 1 is 0. Okay, this is the pattern it was saying. If this is equal to 0, then you know that given X is a power of 2. If you think about it a little bit, it makes sense. At least for the positive cases, we can easily conclude because the bit pattern for 4, for example, right, is, let's take 4, okay? 4 is a 3-bit number, has 1, 0, 0, right? I'm going to show a 4-bit demo, so let me put a 0 in the front. So this is number 4, okay? What is 4 minus 1? 3. 3 means the bit pattern will be this, right? And if you do a bitwise AND between these two numbers, they don't have anything common, so you get a 0, okay? Everything is 0, which makes sense, okay? That means this number X is power of 2, okay? There is one small issue. Okay, when X is 0, I do not consider that as power of 2 because 0 cannot be represented as power of 2. 0 is not equal to 2 power some positive number, right? So on the Microsoft site, they considered 0 as power of 2. Therefore, for them, this particular expression is still a valid expression when they consider 0 can be written as power of 2. Okay. For me, that's not acceptable. So I would like to have a statement that will tell me whether a number X is a power of 2 or not, but without using the if statement. And luckily, Microsoft site also already had a specification, right, which is almost correct for my purpose. It's almost correct except when X is 0. Okay, so now I will show you the site and then we can talk about it briefly. So here is the Rise for Fun site, right? And if you look online for Z3 and search for power of 2, okay, they have a statement here: X is a power of 2 or 0. Okay, there's a caveat here, or 0. If and only if X and X minus 1 is 0. Okay, so the specification that they mention is almost correct because for my purpose, I will not consider 0 as a power of 2, nor did they say that, but they added an extra condition here. You see here, X is a power of 2 or 0, if and only if X and X minus 1 is 0. So what I decided is, I'll take their specification, right, put it into SMT solver, like the program synthesis solver, and come up with another program that will tell me whether the number X is only power of 2 or not. Okay, if I send a 0, 0 is not a power of 2, so 0 should be rejected. That's basically what I wanted to infer automatically. So I'm now going to just simply take the is power of 2 function that they wrote here, right? This is the function they wrote. It takes the input X and it basically uses their SMT syntax, right? X minus 1 is the subtraction part, X minus 1, and bitwise undo with the X, and then they check whether the number is 0 or not. The answer of the expression is 0 or not. Okay, so I'm going to take this whole thing, put it into the program synthesis tool, but I'm going to add an extra condition that this is only true when x is non-zero. And when x is 0, the program that I'm going to synthesize mechanically should give me a 0, because 0 is not a power of 2. So let's get that started now. Okay, I'm going to show you that now. And then we will see how easy it is to mechanically synthesize that. Right? So what you're seeing here is my syntax guided synthesis framework SyGus implementation, right? I'm using this SyGus version 1, but there's a SyGus version 2 I should be migrating at some point in the future. But anyway, that's not the important point here. So this is the usual grammar, right? We said that the program is allowed to use bitwise operations. So whatever bitwise operations are there, we are allowed to use. And I mentioned earlier, one of the scalability tricks is to just keep the bit vector size to be smaller. Otherwise, you get into state space explosion problem. And then you can manually easily make an abstraction of the bit size. Okay, that's what I'm going to do. So I wanted to be able to synthesize this is power of 2 function, right, mechanically. And what is the behavior I'm expecting? The behavior I'm expecting is this, right? This is the spec that I have taken from the Microsoft site. It says when my, well, you know what it says. Basically, it is checking whether x is power of 2 or not. It only works when x is non-zero, okay? But that's okay. That's not a bad news at all. What I did is actually, I'm going to make a claim, right? I'm going to say, if my x is non-zero, right? This is the implies constraint. What am I trying to say is that if my x is non-zero, I would like the inferred program is power of 2 program that I'm going to infer mechanically, right? Which is the program that I don't know how the program will look like, but I want the computer to tell me that program is the same as the spec the Microsoft site gave us, okay? And we know, let's assume we trust the spec, okay? Other than the fact that x is equal to 0, we don't trust that. Other than that, everything is fine, okay? Let's assume like that. But what about x being 0? In the case of x being 0, our is power of 2 function should return a 0, because 0 is not a power of 2. All right, so given this, actually, we can now mechanically synthesize the definition for is power of 2. It may take 1 or 2 minutes, but that's okay. I already did it before I started the recording. As you can see, this is the definition it was inferring. It took 2 minutes or so to infer this definition for is power of 2. Okay, and I can write it for you for just for your information if you're not comfortable with this somewhat cryptic syntax. Basically, what you're trying to do is we are coming up with a function called is power of 2, right? Is power of 2 is the function we are trying to synthesize, and it is defined as follows. It is nothing but the innermost part is x bitwise and with minus x, and then we do we take the x, we logical right shift by 1 position, right? And then we do subtraction, okay? And then the overall answer is right shift by 3 position. This problem, this program solves the problem, and it checks whether a given number x is a power of 2 or not. Okay, you probably noticed that my bit vector size is 4, but that's not a showstopper. Usually, if you look at the constants closely, you may be able to easily generalize it for higher level bit size. For example, if my bit vector size is say 8, all I have to do, hopefully the program will work, I will show you it will work, is by simply replacing the constants. Okay, usually whenever you see bit 1, you leave it as it is. But if you see something like this, okay, in this context, it's clear really, right? You see here it's saying 3, right? Basically this 3, the 3 that you have this 3, right? Now you can compare this 3 with 4, because usually whenever we wanted to get a Boolean answer, 0 or 1, we get rid of the 3 bits, because then we'll have only 1 bit remaining. So we can manually abstract this and generalize it to large bit vector size. For example, a bit vector of size 8, what could have been the expression? So I will claim that this thing is generalizable because I verified it. By just replacing the 3 by 7, we can actually make it to work for all 32-bit numbers as well, right? By replacing number 3 by 31, it will work for all 32-bit numbers as well. Okay, so we can actually check that if you're curious, which I will show you in a minute. So that's basically the main message. Now let's get into the verification part. How do we generalize it, right, to large bit vectors? Usually in C programs, we don't have 4-bit vectors. We have the bit vector size is minimum 8, right? But it's fine. We can just make use of this, right? And let's look into the contract, right? Here is the function that we synthesized just now, right? This is exactly the function. I had copy and pasted it, I believe. Yeah, it's okay. It's exactly the same, except that I have to use an underscore. It's just a little syntax thing. Anyway, so but you see it's the same. And now we can do some small tricks to change this program. Let me give you a little bit context of what you're seeing. What you're seeing is a raw SMT syntax. The first line is what I have inferred using SyGus program inference algorithm, right? Now I'm going to generalize this algorithm for 32-bit representations, right? And I am going to compare against the Microsoft spec, okay? We know for sure when x is not equal to 0, the spec is correct. Okay, so let's try that first. Right, so, okay, I need to add a fact that my x is not equal to 0, right? So how do I do that? I think it's not that difficult. So I just say it is not equal to 0. So I should just put, one moment, I should just put this syntax correct here. Yeah, so my x should not be 0. It is not the case that x is 0. Okay, that's basically what I need to climb, right? Oh, we have so many brackets here. We are climbing that x is not equal to 0, right? Let's check these two things are correct first. Okay, hopefully it'll come quickly. Yeah, so what you're seeing here is that no sat. That means our expression, let me show you the contract, right? Our expression is saying not in the front, right? The sat solver is trying to find an input to satisfy this. It was not able to satisfy. That means the expression is always true, okay, which is exactly what we wanted. Okay, this is good. So let's now generalize this to 32-bit representation, or let's start with 8-bit first, okay? So I'm going to make a climb for 8-bit representation, okay? So this is a small function that converts Boolean into bit vector because we cannot compare Boolean and bit vectors in this framework. Okay, so the simple changes we need to make are like I will use sed. Usually wherever 4 occurs, I will just replace it by 8. This should be fine in this case. Okay, all right, and then some small changes with respect to the bit vectors, right? I claimed that I should just replace the shift amount by 7 in this case, right? So 7, and then this should be good. I hope we can confirm this very quickly. Okay, this is now the algorithm. I want to clarify what are we doing here. This is the line that we mechanically inferred for a 4-bit representation, but then I'm manually generalizing it to an 8-bit representation. And I'm comparing against a known spec, which we assumed it to be correct, right? Except the fact that when x is 0, it doesn't work. As that's the reason why we added this constraint here, that for all x other than 0, these two implementations are same. Essentially, that's what we are trying to confirm. Okay, so let's do that. We have to fix one more thing here. It says 1. We need to make the bit vector size to be proper, otherwise the tool will complain. Okay, so I'm assuming you know a little bit of SMT syntax. Okay, anyway. So that should be good. Now let's try to verify this thing. Yeah, it says unset, which is good, because that means the asserts are always false, which means when asserts are always false, we have a not in the front, right? Which means this whole expression must be true, which is exactly what we wanted. So to sum up the long story short, is that we can actually mechanically derive this expression, okay? But just by specifying the other behavior, we avoided an if then else statement. You can see here there are no if then else statements here, nowhere here. Just a regular bitwise operation. We can check whether a number is power of 2 or not mechanically. We derive this. Actually, we can do one more thing. Now I will show you one more small trick you could play. Let me go back to the Z3 website, right? And load this thing in Z3. Okay. What I'm going to do is basically show to you what happens if I just remove this assert statement that x is x being 0. I removed it. Okay. Now Z3 should be telling us that our program is wrong, in the sense our spec and the implementations are wrong, which is exactly the point here. As you can see, when x is 0, the programs don't match. We can even check which one is wrong, either the spec or the implementation, right? We can call it a spec for a moment. Let's see. So how do we check that? We can use the eval function, right? We are going to evaluate is power 2 spec of x, right? So we are going to check whether what does spec say when we send the x to be 0. A spec says x to be 0 means 0, which is well, I should have used this to be implementation, because we took the Microsoft code as a spec. Anyway, now we can check that the spec will be saying 1, which is wrong, because I talked about it earlier. When x is 0, we cannot use x and x minus 1 to decide whether a number is power of 2 or not, which is clearly coming now. So that's basically it. What I did actually is two things today. Let me summarize it. What we did is we basically derived is power of 2 function mechanically, right, using this SyGus syntax guided synthesis algorithm. All we did is we basically specified this possible grammar operations that we allow the system to use. The no if then else statements here. And we also gave that a searching algorithm a spec, okay? And the spec is kind of partial spec. We didn't cover the scenario for x being 0, but we gave a counterexample here. When x is 0, when I say counterexample, I meant to say when x is 0, we want the behavior to be 0, that the program returns 0 for us. Other than that, the spec and the is power of 2 must be matching. That's basically the general specification for all possible x's, okay? And that's what we did. And then we manually generalized the generated formula to 8-bit representation, and we mechanically verified using SMT directly that those two programs are correct, meaning the spec and the implementation are correct. That's basically what we did. Okay, that's all. Thank you very much for your attention.